ever try to, like, divide something perfectly, without a ruler. Today's deep dive is going to give us some tools to do just that.
Okay.
We're diving into chapter 11 of that math textbook, all about geometric constructions. And trust me, this goes way beyond just drawing lines on paper.
Right.
It's about understanding the why, the elegance behind these techniques.
Yeah. What's so fascinating is that, these constructions, they were the tools of the trade for mathematicians and architects, centuries ago.
Oh, wow.
Long before calculators or CAD software. It's about using the inherent properties of shapes themselves to solve problems.
That's so cool. So let's unpack the first challenge, dividing a line segment in a specific ratio without using measurements.
Okay.
Our source material uses the example of a 3.2 ratio. So imagine trying to perfectly divide something into 5 parts.
Yeah.
But you're only using a compass and a straight edge.
Right. So this is where the power of parallel lines comes into play. It might seem surprising, but those parallel lines are really key to unlocking proportions.
Interesting.
The textbook calls this the basic proportionality theorem. Essentially, if you have parallel lines that are slicing through a triangle, they create segments that are proportional to each other.
So by creating these parallel lines, we're kind of setting up this geometric puzzle that forces the line segment to divide in the ratio that we want.
Exactly. It's like a geometric proof playing out right in front of you.
I like it.
The method starts simply enough. You draw a second line, and any acute angle will do, extending out from one end of the segment that you actually want to divide.
And then we mark off a certain number of segments on that new line.
Exactly. And since we're aiming for that 3.2 ratio, we would mark off 5 equal segments.
Okay.
And this is where that connection between, the ratio and the construction becomes so clear. Then you connect that last point back to the other end of your original line segment, creating a larger triangle.
So we're kind of trapping our original line inside this bigger triangle.
Yeah.
But those parallel lines have to come back into play, right?
They do. And remember, we want a 3.2 ratio. So
Okay.
from the third point that you marked on that angled line, you draw a line that's parallel to the base of the big triangle.
Gotcha.
And it will intersect your original segment, dividing it perfectly in a 3.2 ratio.
Wow, that's seriously clever.
Yeah.
It's like the parallel lines are guaranteeing those proportions. No measuring needed. Now, the textbook also mentions similar triangles, which feels like a whole other level of geometric wizardry.
It builds on those same principles, but takes things a step further.
Okay.
Instead of just dividing a line, now we're constructing entire triangles that are proportionally identical.
Okay.
This is where that idea, a scale factor, comes in. And it's simply the ratio between corresponding sides of those similar triangles.
So if you wanted to create a miniature version of a triangle, but keep all the angles and proportions the same, you would use a scale factor less than 1. Right?
Exactly. Let's say you want a similar triangle that's 34 the size of the original, like one of the examples in the text. You would start by drawing a ray from one vertex of your triangle, just like we did before. But instead of marking off 5 segments, this time we're focused on the numbers 3 and 4 because our scale factor is 34.
Okay, I'm seeing a pattern here. We mark off 4 segments on that ray. Since 4 is the larger number in our ratio, then what?
You connect the fourth point that you marked back to the opposite vertex of your original triangle.
Okay.
Now you have this larger similar triangle that encompasses your original one.
Right.
To get that smaller triangle with the 34 scale factor, you draw a line parallel to the base of this larger triangle, starting from the third marked point on your ray.
Okay.
And where it intersects the side of your original triangle, that's your magic dividing point.
It's like we're using those parallel lines to pinch the triangle down to the exact size we need.
And you can do the reverse, too. If you use a scale factor larger than 1, like 53, you can construct a larger similar triangle using those same principles.
So we've tackled how to scale triangles up or down.
Right.
But what about constructing those lines that, just graze a circle at a single point?
Yeah, those are tangents.
Yeah.
And they have some pretty cool applications.
Oh, yeah.
Oh, yeah, in the real world.
Like what?
Well, think about gears meshing together in a machine.
Okay.
Or even how a ball bounces off a curved surface.
That's true.
Understanding tangents is key to designing those interactions.
Yeah, that makes sense.
Our source material actually goes into a method for constructing tangents to a circle from a point outside the circle.
Okay, and just to be clear, we're talking about drawing not one, but two tangents from a single point outside the circle.
You got it.
Okay.
It's like, drawing those like perfectly aimed pool shots.
Okay.
Where the cue ball just grazes the target ball at, the exact right angle.
Right.
And the beauty is we can do all of this with just a compass and straight edge.
I know. It's always amazing to me how much we can get done with those two things.
Yeah.
So walk me through it. Like, where do we even begin when we're constructing these tangents?
Well, we start by connecting the center of our circle to that point outside the circle.
Okay.
This line is going to be our guide.
Oh.
It's almost like an axis of symmetry for the entire construction.
Okay. So we're essentially drawing a line that, like, pierces through the heart of the circle and extends out to our point of interest outside of it.
Exactly. Okay. What's next? The next step is to find the midpoint of that very line.
Okay.
It's like, perfectly folding it in half.
Okay.
To find that center crease, and this midpoint is going to become the center of a whole new circle.
Oh, okay. So now things are getting interesting. So we're constructing a circle within a circle.
We are.
And what determines the size of this new circle?
Great question. The radius of our new circle is going to be the distance from that midpoint we just found to the center of our original circle. So it's going to be, a larger circle that overlaps with our original one.
Got it. So I'm picturing it now. It's like two circles having a little overlap moment.
Exactly.
I bet those points of intersection are important.
They're very important. Those 2 points where our circles intersect, those are our points of tangency.
Meaning if we were to draw lines connecting those points back to that original point outside the circle,
we would have our 2 perfectly constructed tangents.
Oh.
It's like, a little geometric magic trick, but of course there's like solid reasoning.
Oh, I'm sure. There always is.
Oh.
So what's the geometric secret behind this construction?
It all comes down to right angles and the properties of semicircles.
Okay.
Remember that first line we drew?
Yeah, our axis of symmetry line.
Exactly. When we drew our second circle, using the midpoint of that line,
right,
we created 2 semicircles that share that very line as their diameter.
Okay, I'm seeing it. So our 2 tangent lines are actually line segments that live within those semicircles.
Exactly, and here's the key. Any angle inscribed in a semicircle, meaning like all 3 points touch the arc of that semicircle.
Okay.
Has to be a right angle. It's one of those like elegant geometric truths.
So by constructing those semicircles, we essentially force the angles where our tangent lines meet the circle to be 90 degrees.
Yes.
Clever.
And a line that intersects a circle at a 90-degree angle to its radius, that's the very definition of a tangent line.
It's amazing how everything comes back to those like fundamental geometric principles.
Huh.
This feels like a good point to like shift gears though.
Okay.
We've covered a lot of ground from like dividing lines to scaling triangles, even constructing these tangents. It's like we've like been given this glimpse into the toolbox of a geometric mastermind.
Right.
But what happens when we take these tools and like step outside the flat world of, 2 dimensions?
Yeah.
We're working with lines and triangles.
Right.
But like the real world, it's full of these 3-dimensional objects.
Yeah. It's a fascinating thought.
It really is.
Isn't it? Yeah. Like imagine needing to divide a rectangular prism into like specific ratios of volume.
Okay.
Not just area.
Right.
Or picture an architect scaling up a model of a skyscraper, but they have to maintain those perfect proportions.
That's like a whole other level of complexity. Would those challenges require like completely different geometric principles? Or could we like adapt the techniques that we've already, explored?
Great question.
Like, could we use parallel planes, for instance, to divide like the 3-dimensional shape in a specific ratio? Like we use parallel lines to divide a line segment.
That's very interesting. It is a question worth pondering.
Right.
Could we, extend this concept of similar triangles to similar pyramids or prisms?
Yeah.
What would a scale factor even look like in those cases?
That's something for our listener to chew on.
There you go.
Right.
Yeah.
Maybe they'll like be inspired to grab their compass and a straight edge, maybe even some clay or building blocks, and start experimenting. I mean, that's how new discoveries are made.
Exactly.
By like pushing those boundaries of what we think we know.
It's a it's a good reminder that even in a world that's, dominated by all these digital tools, computer modeling, the elegance and the power of classical geometric construction it still holds up.
It does.
There's a certain satisfaction to it.
Oh, for sure.
To solving problems with just, a compass and straight edge.
Yeah.
Relying on that pure geometric reasoning.
Yes.
To, guide the way.
It's like uncovering this, hidden language.
It is.
Of shapes and proportions.
It really is.
And on that note, we'll wrap up this deep dive into the world of geometric constructions. We hope you've enjoyed this journey of, lines and angles and geometric ingenuity. Thanks a lot, Tom.